Good morning, good afternoon, and good evening. Thank you for attending this molecular communications workshop, and thank you for the kind introduction from the session chair. As shown in this title slides, my name is Nan Yang, and I'm currently working at the School of Engineering at the College of Engineering and Computer Science in the Australian National University. It's a great pleasure for me to share some of my results in molecular communications with every attendees here. And also, I would like to express my sincere thanks for all the attendees, for your courage and for your interest to jump into this promising and highly beneficial nanoscale communication paradigm, molecular communications. So the title of my talk today is regarding cooperative molecular communications, in which I'm going to talk about how should we consider a number of transmitters and or receivers in the molecular communication systems. And I'm going to share the results regarding modeling, analysis, and optimization with this cooperative molecular communication paradigm. So before I go forward, I would like to sincerely express my thanks to my previous HDR students and my collaborators, including Ms. Yuting Fang, Ms. Xingyu Huang, Ms. Yiran Wang, and my collaborators, Assistant Professor Adam No and Professor Andrew Eckford. All the contents that I have presented here are in the collaboration with them. So here is the outline of my talk today. In the first, I will give a brief introduction to molecular communication for the sake of completeness. And after that, I'm going to introduce several of my existing research contributions in molecular communication. So in section 2, I'm going to introduce two of my research works in cooperative molecular communication. And after that, I'm going to talk about how we characterize the number and behavior of cooperators in quorum sensing. And after that, I'm going to introduce a recent work on the one-dimensional molecular communication with two absorbing receivers. And after that, I'm going to talk about the simulation algorithm for absorbing receivers. And finally, I will bring a few future directions to trigger future collaboration and trigger the future works to extend my existing contributions. So let's start with the introduction to molecular communication. Given that this is a molecular communication workshop, I believe that almost all the presenters will talk about what the molecular communications is. And here I would like to briefly share my point of view and will not spend too much time on that. So what is molecular communication? And here I use MolCom to represent molecular communication. And I would like to see this kind of name can be used in the community. So molecular communication is a communication paradigm which mainly happens in the nanoscale or microscale in the natural systems. Typically, let's think about how do the biological systems share the information. So here I give like a picture, and we know that in the biological system, for example, inside the human body, we always have molecules, and molecules are commonly used between different cells, between different tissues, and between different organisms. So in this case, what is molecular communication? I would like to bring a biological example to show that. So the example that I'm going to use here is borrowed from Nariman's survey paper published in 2016. And to be honest, I'm not sure if someone else will use the same example. And for this example, we consider like a process inside the human body, which is the neuromuscular junction. We call it NMJ. So in the figure, we can see, in the figure, the neuromuscular junction talks about the process between the nerve cells on the top of this figure and the muscle cell on the bottom of the figure. And in the nerve cells, it contains a number of, or maybe a large number of vesicles, which contains acetylcholine, and we call it ACH molecules. So in the neuromuscular junction, the motor neurons release the ACH molecules. And as we can see here, the molecules are released from the nerve cell, and these molecules diffuse within the environment through the synapse and bind ACH receptors. So in this case, in order to keep the communication between the nerve cell and the muscle cell, we can see that the muscle cell has the acetylcholine esterase, and it will, clean the ACH cells, and for example, it may destruct the ACH cell. And at the same time, we can see something as being absorbed into the muscle cell and something has been released back to the environment. So this is an example from the human body, and this is an example of the molecular communication. And we want to use this example to tell everyone that, okay, molecular communication actually exists in our nature, inside our body, and our job is to investigate the principle behind this molecular communication paradigm and see how we can use it into our current, emerging, and the future nanoscale applications. And based on this, let's see the basic principle or basic mechanism of molecular communication. So what is molecular communication? In molecular communication mechanism, the information transmission between two devices or two nano machines is realized via the exchange or propagation of molecules. So here I give a figure to show the process. In this figure, we can see we have a transmitter, which is a type of nanomachine on the left-hand side. We also see a receiver, which is another type or same type of nanomachine at the right-hand side. At the transmitter, we have a particle generator or molecule generator. So through some chemical reactions, the molecules have been generated within the transmitter. And these molecules can carry information. And after some mechanism, which we call emission or release control, these molecules are released by the transmitter. And after being released, these molecules leave the transmitter and propagate within the environment. In molecular communication, typically we consider a liquid environment, and sometimes we consider a gas environment. And for this environment, the molecules propagate according to some natural properties. For example, the free diffusion, or it has been transported by some motor, or it has been, it has propagated with the impact of different kind of flows and chemical reactions. But whatever the propagation environment is, the molecules are received by the receiver. So they arrive at the receiver and they are captured, or they are received by the receivers. And then we have a decoder, somehow like some process which has a similar function of decoding to process the received signal or received molecule and sees the information carried by these molecules. And this is the function of the receiver. So we can see that for the whole mechanism of the molecular communication, similar to wireless communication systems, we have a transmitter, we have a receiver, but there is a fundamental difference in which in molecular communication, the molecules are the medium or are the particles which carry the transmission. So how are the molecules transported? As what we have mentioned in the previous slides, the molecules propagate within the environment from the transmitter to the receiver. And it is very often in the early studies in molecular communications that we do consider the molecules are propagated according to free diffusion, or sometimes we call it Brownian motion diffusion. And in this case, the molecules are transported within the transmitter. And the advantage of this free diffusion or the propagation of molecules is that we do not need the external energy to transport these molecules. In this case, it would be very suitable to be considered and applied in a nanoscale communication, because in nanoscale communications or nanoscale applications, actually, it is very, very challenging to consider that we have to provide external energy, for example, from using the battery to support the transmission. So in this case, the free diffusion of molecules does not require any external energy. And given this case, the transportation of molecules have been used by many processes in cells, for example, the quorum sensing, in which we are going to introduce at a later section. And apart from free diffusion, recent works have also considered some other propagation mechanisms. For example, they may consider that the molecules are propagated through the active transport, or sometimes their propagation in the environment are affected by the physical properties of the environment. For example, the boundary of the channel, the different kind of flows, and the chemical reactions and the obstacles within the environment. So the propagation of molecules are also an important, research topic in the molecular communication. But here we just consider that the molecules can be propagated, and mainly it is subject to free diffusion in the environment. And as we briefly mentioned, there is a significant difference between molecular and the molecular communication and the existing or conventional wireless communication, or we call it electromagnetic communications. So the key differences between the molecular communication and electromagnetic communication are summarized in this table. We can see that for the signal carrier, the wireless communication or EM communication typically use radio waves at a central frequency to carry the signals. But for molecular communication, they use molecules to carry the information. And for the speed of communication, the wireless communication is performed at the speed of light, which is 3 × 10⁸ meter per second. But for molecular communication, the speed is typically very, very low. And based on the current studies, the speed of molecular communication is on the order of micrometer per second. When we say micrometer, it is like 10⁻⁻⁶ meter per second. For the communication range, there is a huge difference. For wireless communications, the communication range is from like a few meters until 1 or 2 kilometers. And even for some like more advanced wireless communication systems, we also consider, tens or even hundreds of kilometers for the communication range. But for molecular communications, the range is from a nanometer to micrometer. So in this case, the range of molecular communication is very, very short compared to the wireless communications. And for the source of the noise, again, there is a huge difference. For the wireless communication, the noise typically comes from electromagnetic fields and different kinds of signals sent by other transmitters. But for molecular communication, the noise typically comes from the Brownian motion of different type of molecules, especially the unwanted molecules, as well as the chemical reactions which may be performed within the environment or at the different transmitter or receivers. For the encoded information, typically wireless communication is used to encode the information such as the voice, the text, the video, and the data. But for molecular communication, it is typically used to transmit some chemical state, some phenomenon, and some biomedical or biological processes. Lastly, for the consumed energy, wireless communication consumes a very high level of energy compared to molecular communications, while molecular communications consumes a very low level of energy. So in this table, we show that molecular communication and wireless communication have fundamental differences between each other. And in this case, although we know that molecular communication also transmits signal wirelessly, but given this fundamental difference, the techniques, the frameworks, the existing results and the methodologies in wireless communications typically cannot be directly used in molecular communications. We may borrow some ideas from the wireless com, but the methodologies over there cannot be used in molecular communications. And in this case, we have to develop new analytical framework, build up new models, and perform new performance analysis, design, or optimization for molecular communication. And that imposes a significant, pressing, and complex challenge for the molecular communication scientists. Based on the difference, we can see the molecular communication have some unique features. For example, we've mentioned that the molecules propagate according to free diffusion. And in this case, there is an uncertainty in the diffusion trajectory of each molecule. At the same time, for the environment where the molecular communication happens, we have to consider environmental phenomena, for example, the chemical reactions and the fluid flow in the environment, such that the modeling of the molecule propagation has to be practical and can guide the use and design of molecular communication system in practice. Apart from that, we also need to consider some hardware or constraints at the tiny devices or nano machines. For example, in molecular communication, typically we say that the nano machines can be modified cells or artificial cells. And in this case, because they have the very, very tiny size, in this case, they have limited computational resource that can be used, such that we have developed the relatively simple communication and signal processing algorithms at these devices, such that they can be used in the future nanoscale applications. And then in terms of the simulation, although typically we use MATLAB or some other platforms to simulate the performance of molecular communication, but we have to use a particle-based simulation method in which we have to assume or model the location of a molecule using the equation that I provide here. So in this equation, you can understand that the location of a molecule at time I, where we consider, if we consider a three-dimensional environment, it has three coordinates, xi, yi, and zi. And in this case, it is given by the location of this molecule at time I-1 plus the incrementals at the x-axis, y-axis, and z-axis. And for each of them, the incremental in the location or distance follows a Gaussian distribution with a zero mean and a variance of 2d times delta t, where d typically is the diffusion coefficient. It tells like how fast or how slow the molecule is diffused within the environment, and delta t is the time interval, which is the duration of the time. So given this, we want to ask a question: why do we conduct research in molecular communication? So why do we, try to advance the area of molecular communication from the communications and the signal processing perspectives? Because we always believe that molecular communication is a promising and highly useful communication paradigm for the future nanoscale communications and for the future Internet of Nano Things. So in this case, our results can help to understand the different kinds of biological systems, and our results can help us to interface and interact with biological systems. And finally, based on this deep understanding, our results can help us to gain the inspiration for design of synthetic networks. For example, we always talk about the Internet of Nano Things, where the nano-sized machine, the nano machines or nano things should be connected with each other and jointly perform some complex tasks. So the Internet of Nano Things will have different kind of applications, and we would like to say, to construct this Internet of Nano Things, we need nanoscale communication. And compared to other nanoscale communication paradigms, molecular communication is important communication paradigm to support the exchange, the transmission, and the reception of information at the nanoscale. That is why, from the communication and the signal processing perspectives, we have to investigate molecular communication. I can see that Ian Shah will deliver a talk in Internet of Nano Things in the next few days, and I believe she will talk more about how can we use molecular communication to support the IoT and its applications. So in order to do that, we are able to see some promising applications can be brought from imagination to reality. For example, with the mature Internet of Nano Things, we are able to construct the intra-body health monitoring and disease detection. For example, we can use nano machines to timely detect the disease which has happened within the human body, and this will help us to prevent the growth of the disease from the early stage and help to identify the disease and extend the life expectancy expect like to increase the life of human bodies. So this is the benefits of the health monitoring and disease detection. Apart from that, we can also use nanomachines to help targeted drug delivery. For example, we can use nanomachines to identify the location of the unhealthy part within human body, for example, the location of a tumor, and then we can use these nanomachines to notify the location of the tumor to other nanomachines, especially the nanomachines which carry drugs, and this will help these nanomachines to carry and deliver the drugs to the precise location of the tumor without affecting other parts. So this is how the molecular communication and the Internet of Nano Things can facilitate the targeted drug delivery. Apart from these healthcare and medicine applications, molecular communications and Internet of Nano Things can also help with other applications. For example, the environmental monitoring, and it can help to avoid the, to detect the water quality, can avoid the pollution in the environment. So for all these kind of things, the molecular communication is a very, very promising communication paradigm, and it has huge potential for future use in different kinds of applications. So that's why we want to build up the fundamental theory of this communication paradigm and advance this area. And ultimately, we hope that our results can bring the different kinds of applications into reality. So what are the typical molecular communication research challenges? And definitely from different perspectives, from different research groups, we have different, research challenges that we have to tackle. And from my perspective, I just list two research challenges that we want to tackle in our research. But definitely these two challenges are not the sole challenges that we have to deal with. There are quite a lot of different challenges, and I believe all the other outstanding researchers will talk about the challenges from their perspectives. So the fundamental research challenge that we want to tackle in our research is to address the low reliability. We know that for molecular communication, the communication is performed through the free diffusion of molecules. This results in a relatively poor reliability. So in this case, how can we improve the reliability of molecular communication system? That is a key challenge and fundamental challenge that we want to address. So in this case, one promising solution which has been proposed by our studies is to transmit information from multiple nanotransmitters and then combine or jointly evaluate the received information at multiple nanoreceivers. So this is the motivation behind the exploration of a key idea we want to present in this work, which is cooperative molecular communication. Apart from reliability problem, we also want to evaluate the performance limit of the molecular communication systems, which includes not only reliability, but also other factors such as the transmission rate, such as the energy consumption. And in this case, when we want to produce a specific molecular communication strategy, we would like to ask ourselves, what is the best error performance that can be achieved by the proposed strategy? And in order to investigate the best error performance, obvious we are able to do the simulation to do that, but at the same time, we want to reduce the burden. Incurred by this kind of simulation. And in this case, the evaluation of the best error performance needs a novel and generalized analytical framework and optimization algorithms. As I mentioned, this framework has to be somehow established from scratch because the existing results in wireless communications cannot be directly applied. And apart from the analysis, this framework may also help us to understand, to predict, and possibly control and manage the behaviors of nanomachines in practical environments. So here we talk about two research challenges which we are going to tackle in this talk and in our previous studies. One is low reliability, one is performance. And in the following, we are going to introduce a few studies to talk about what are our efforts and what are our contributions to address the reliability and the performance limit challenges. So now let's look at the first work that I have been doing for cooperative molecular communication. So let's start with modeling. And in the first work of cooperative modeling, as we mentioned, we would like to explore the benefits of using multiple receivers to enhance the reliability of the molecular communication system. So in this first work, we can see the assist model like this. So there is a transmitter, and the transmitter sends signals or sends molecules to different receivers, and then the different receivers will report the signals to a fusion center, we say FC. So in this case, it is clear that the communication can be divided into two phases. In the first phase, the transmitter transmits molecules to the number of receivers, and here we assume there are k receivers. And in this figure, we can see the k equals 5 for as an example, but definitely in the paper, we can see the k is a arbitrarily integer. So for the first phase, where the communication is happened from the transmitter to the receiver, the transmitter uses on-off keying to transmit. So here, on-off keying is a simple modulation scheme in molecular communication, where the transmitter sends a bunch of molecules if the transmitter would like to transmit one, but the transmitter would remain silent, which means the transmitter does not transmit anything if the transmitter wants to send out a bit of 0. So in this case, when the transmitter would like to transmit one, it transmits type A0 molecules, and these molecules diffuse within the environment. And for each of the receiver, we assume that in this work, in the first phase, each receiver would make a local and hard binary decision. That means the receiver will count the molecules it receives from the transmitter, and then the receiver would make a decision of either 0 or 1 based on the received molecules. And in the second phase, the receiver would transmit their decisions to the fusion center. Again, for each receiver, it adopts the on-off keying as well. So in this case, if the transmitter K, it would like to transmit a bit of 1, it will transmit type AK molecules that diffuse into the environment. And then at the fusion center, we adopt an N out of K rule to determine the transmitted signal from the transmitter. That is, the fusion center will detect the decision transmitted by each of the receiver. And then for each of the receiver, because in total we are going to have K decisions, the fusion center would make a decision of 1 if it receives at least N decisions. So N out of K is a general majority rule, and if N equals K, that is a AND rule, which means AND rule or AND rule, which means the fusion center would make a decision of 1 as long as all of the receiver would transmit 1. But apart from that, if N equals 1, then that can be considered as an OR rule, which means the fusion center will make a decision of 1 if there is at least 1 decision which is received from the transmitter. And for the general case, we consider an N out of K rule, and we call it a majority rule in this figure. So considering this system model, we assume that the receivers in the fusion center are passive receivers. In this case, these receivers do not interact or do not react with the molecules. They only count the number of molecules within itself. And for each transmission interval, we consider there are multiple samples. Here, the sample means the receiver or the fusion center will count the number of molecules inside the observer. So here is the figure showing the observations. So assume that there are Lth symbol interval, and within each symbol interval, it has a duration of t, and it consists of this kind of process, which we have given in the second part of this figure. So for each interval, for example, we take the jth symbol interval as an example. At the beginning of this interval, the transmitter transmits a symbol. We call it W transmitter J. And then the receiver will take different samples after the transmission, and then it will make a decision. And we call the duration from the transmitter release or transmit the signal and before the receiver transmits its own signal as T trans. And after that, the transmitter K will transmit the received signal, will transmit the received signal, and after that, the fusion center takes samples, and we call the second part of the duration as T report. So this is the process within each signal interval. And for this case, we have performed analysis and optimization to investigate and to optimize the received performance. So the key performance metric that we consider in this work is the global error probability. And here we give the general expression of the global error probability. It is given by P1 times the QMD, where QMD is the misdetection probability, and plus E minus P1, and then times QFA. Then QFA is the false alarm probability. And then because we can see the K receivers, and the fusion center will use N out of K rule. So in this case, the expression for the misdetection probability and the false alarm probability are given in these two expressions. And definitely they are just, general expressions, but in the paper we have provided detailed analysis about how to analyze the QMD, how to analyze QFA, and how to, perform the detailed derivation to receive to reach the results. So by deriving the approximate results of these expressions, we formulate a convex optimization problem to minimize the global error probability that we have considered here. And then we solve the problem and optimize the average error performance. So I have to say that in this presentation, what I would like to do for each of the research work is that I just would want to introduce the motivation, the system model, and the key results and the methodologies we use in the paper, and followed by the numerical results. So for all this detailed analysis and optimization, because they are mathematically complicated, I would like to encourage anyone who are interested in this derivation to look at the relevant sections in our publication for the detailed analysis. But in the presentation, and for the sake of brevity, I just ignore the detailed analysis of the optimization. So here I just want to show that we derive these results, and we perform mathematical analysis to reach some approximate results, and then using these approximate results, we formulate and solve a convex optimization problem to minimize the global error probability. So this is the key analysis and optimization that we have been doing in this work. And after that, I just want to show a few numerical results we have obtained in this work. So in this figure, we plot the best or minimum global error probability against K, which is the number of receivers for different rules. So here we have transmitter to fusion center link, which means we do not incorporate any receiver into the system. And we also plot the N rule, which means N equals K. That means we have to consider K out of K decisions. We have an OR rule where N equals 1, and we also have the majority rule where we consider the optimal N out of K. So in this case, we can see that for a fixed total number of molecules, in which we assume that the number of molecules released in the environment is the same, we can see that the error performance improves when we have a higher number of receivers. And after that, we find that compared with the TX transmitter to fusion center system, which is the straight line, we find that the cooperative molecular communication system achieves a better performance than this direct link without the help of receivers. And then we compare the error performance of these three rules. Definitely we find that the majority rule, which has the maximum generality, has a better performance than the two extreme case, the N rule and OR rule. And finally, we also see that our analysis meet the simulation points, which shows the accuracy of our results. And after that, we would like to explore how we can further define or design the detection mechanism in this cooperative molecular communication system. So in this case, in the second work in the cooperative molecular communication, we would like to consider the impact of maximum likelihood detection. Again, in the system model, we can see a similar system model where we have a transmitter, we have a number of receivers, but in this figure, we just use an example of 2. But in the paper, we can see the multiple receivers, and then we consider the fusion center. Again, the communication can be divided into 2 phases. One is the first phase, and one is the second phase. In the first phase, the transmitter release molecules to the receivers, and in the second phase, the receivers release the molecules to the fusion center. But here we can see the more complicated communication process in the second phase. So here, if we use D to denote making decisions, and A denotes amplify the observations. So in this system or in this work, we can see the 3 strategies to facilitate the second phase transmission. So the first one is MDML. For MDML, the receiver will adopt decode and forward protocol, which means the receiver make the decision about the transmitter, the signal. That means in this case, the receiver will make a decision of 1 or 0 and then transmit this 1 or 0 using multiple type of molecules. So MDML means multiple type of molecules, and then the fusion center will use maximum likelihood decision to detect the signal. So this is the first strategy, MDML. In the second strategy, we say it is SDML. So for SDML, the receiver will also use decode and forward protocol to deal with the received signal, but all the receivers will use only a single type of molecules to transmit. And in this case, the fusion center, and then the transmission means that the receiver, all of the receivers will use the same type of molecules to transmit. Again, the fusion center will use maximum likelihood detection to deal with the received signal. And then the third strategy we are considering here is called SAML. So SAML means that the receiver will use amplify and forward to deal with the received signal. That means the receiver does not decode the signal from transmitter, but just amplify the received molecules and forward these molecules to the receiver. And all the receivers will use the same type of molecules to notify the results. Again, for this strategy, the FC will use maximum likelihood detection to detect the received signal. So by comparing these 3 proposed strategies, MD, SD, and SA, so M and S denote how many types of molecules we use in each of these strategy, and D or A denotes like what is the operation at the receiver. So in this case, we can see MDML, SDML, and SAML corresponding to different operation mechanisms at the receiver and different types of molecules adopted by different receivers. And based on these principles, we can easily see that for the complexity comparison, the MDML has the highest complexity because it uses decode and forward operation, and also it requires multiple types of molecules. And then SAML has the lowest complexity, and SDML is in the middle. And then by introducing these 3 strategies, we have derived the detection rules. So for this case, we derive the general detection rule in the jth time interval is given by these expressions. So for SAML, the simplest one, we derive the general detection rule given by this. And then if the receivers use decode and forward, and then we derive the general detection rule for the SDML and MDML strategies using this equation. And here we define this L function in terms of this is the probability that the observation at the fusion center in the jth interval, given some observed or received signals. And here, in order to perform the maximum likelihood detection in the current time interval or current symbol interval, definitely we know that it requires knowledge of the previously transmitted symbols by the receiver, as well as the symbols from all the receivers if the receiver adopt decode and forward strategy. And also in this work, apart from considering the 3 communication strategies, we consider 2 different cases. One is that we assume the perfect knowledge of the previous symbol is obtained. And the second is that the estimated knowledge of the previous symbol is received. So in this case, we can see the perfect knowledge of the previous symbol tells us what would be the best performance that we can achieve by using the maximum likelihood detection. And the estimated knowledge of the previous symbols gives us the behavior of this mechanism in practical scenarios, because the estimated knowledge can be accurate and can be inaccurate. And after that, we analyze and optimize the error performance for each of the strategy. Again, it involves complicated analysis and optimization. So here we skip that and go directly to the numerical results. In these numerical results, we plot the optimal average error probability against the number of receivers for these different kind of communication strategies. So here, let's just say, look, for example, if we look at the figure on the right-hand side, we compare our three strategies, SAML, SDML, and MDML with the majority rule that we considered in the first work that we just introduced before. Again, apart from observing that the average error probability decreases with the increasing number of receivers, we can see that by using the maximum likelihood detection, the SDML and MDML would achieve a better performance than the majority rule that we consider in the previous work. And this shows the benefits of applying the maximum likelihood detection in the cooperative molecular communication system. And then we can see that if the receiver is using amplified forward and using a single type of molecules to transmit, it achieves the worst performance. And this is not surprising because it has a lowest complexity. But compared to the majority rule that we consider in the previous work, the SAML also achieves a lower requirement because it only needs amplified forward at the receiver, which is a relaxation compared to the majority rule. At the same time, all the receivers use the same type of molecules. Again, it uses less molecules, or it reduces the complexity at the nanomachines compared to the majority rule. So this is how the figure tells us. And after that, we also consider the impact of different locations of receiver 1 while considering a fixed location of receiver 2 and plot the different error probability in different figures. So we can see the different locations, and we can see that for some of these locations, the error performance will typically reduce and then increase when we increase the number of molecules released by the first receiver. And this shows the accuracy of our analysis, and also it gives some insights about what would be the optimal number of molecules released by the receivers if we want to minimize the error probability. So this is the insights that we can obtain from this figure. So by considering these works, we have produced two different studies in cooperative communication. We consider similar system setup where multiple receivers are used to help the transmission from the transmitter to the fusion center. But here in the first work, we establish the fundamental of the benefits of cooperative molecular communication, where we consider the benefits brought by the majority rule. And in the second work, we consider different transmission strategies in the second phase of the communication, and we explore the maximum the benefits brought by the maximum likelihood detection into the molecular communication in terms of reliability improvement. And these two works, I would like to say, have formed the basis of exploring the fundamentals of fundamental principles of cooperative molecular communications. So here is the brief summary about these two works. So after these two fundamental works about cooperative molecular communications, what we have been doing is that we want to expand the concept of cooperative molecular communication into a more practical scenario. And then we would like to do something different to look at the potential benefits of cooperators or cooperative molecular communication in practical nanoscale scenario. So this leads to this work that I'm going to introduce now, which is the characterization of cooperators in quorum sensing. And for this work, we would like to first introduce what is quorum sensing. In quorum sensing, which is a natural phenomenon, the bacteria assess population density by releasing and recapturing molecules in the environment. So here in this figure, we give an example about a low cell density and a high cell density. On the right-hand side, we give a low cell density. And in this case, a bacterium contains a receptor with a target genes. And then it also contains a side face, which can release molecules where we use this red diamond symbol to represent signaling molecules. If we have a low cell density, that means we don't have too many bacteria. Then typically bacteria do not cooperate with each other. But if we have a high cell density, then we can see that all these kind of bacteria will release molecules to the environment, and then they will recapture these molecules, no matter these molecules are released by themselves or released by the other bacteria, it does not matter. And then the bacteria release the molecules and then bind with these molecules, and then these molecules will diffuse into and out of the bacteria. So important thing is that in quorum sensing, the bacteria will decide to cooperate with each other if the received or recaptured molecules is higher than a threshold. So this is the basic principle of quorum sensing. So in one sentence, we have a group of bacteria and they release and recapture the molecules. If the molecules that they captured is higher than the threshold, they will decide to cooperate. So this is the basic principle in quorum sensing. As we mentioned, when the density of bacteria increases, which means we have a larger and larger number of bacteria, the received molecules at each bacteria would increase. And if the number of molecules that exceed a threshold, the receptor of the bacteria is activated. So this bacteria becomes a cooperative bacteria, and its receptor is activated to regulate the genes for a cooperative response. And these bacteria will become cooperative bacteria. So in this case, when we consider a scenario with a high cell density, some of the bacteria may become cooperated, and this would bring benefits, and this phenomenon exists in nature. As we mentioned, quorum sensing coordinates many collaborative activities in nature, and here I'll give two examples. One is biofilms. For biofilms, the bacteria form communities. For example, they can form the communities from the basic bacteria, and then they form in groups. So the bacteria form in communities in biofilms, and this is one of the resistance mechanisms used by the bacteria to survive in the presence of antibiotics. And if we can do some research in quorum sensing and investigate the behavior of these biofilms, we are able to find the mechanism of this bacteria survive in the presence of antibiotics. So if the survival of bacteria is good, then we try to maximize its probability. But if the surviving is a bad behavior, then we try to mitigate this kind of probability. And the second example we want to show in the quorum sensing is the bioluminescence. For this bioluminescence, it means the production and the emission of light by a living organism. So this can be used to help us for the detection of the environmental pollutants and the contaminants in the foods. So this is the example of the bioluminescence. And if we can see the lights from the gathering of this bacteria, it can tell us something, and this can help us to detect, for example, if there is any pollutants in the environment. They can help us to do that. So in this case, quorum sensing is important in practical scenarios, and we would like to extend the concept of cooperative molecular communication to help us to categorize the cooperators. For example, what is the probability for the bacteria to cooperate, and what will be the expected number of cooperative bacteria in an environment? This will help us to gain further insights into the quorum sensing. So in this system model of this work, we can see a unbounded 2D environment. For the sake of simplicity, we can see the 2D environment, and it is unbounded. And then in this unbounded 2D environment, we can see a population of bacteria, and they randomly distributed in a bounded circle. So the environment is unbounded, but the bacteria, they are distributed within this bound. And for this bacteria distribution, we can see a 2D spatial point process with a constant density. So the density decides like how many bacteria they are distributed within this given bounded circle. And as we mentioned, according to the principle of quorum sensing, each bacterium acts as a point receiver and a circular passive receiver. So it releases molecules, and then it also recaptures molecules as the transmitter, as the receiver. And in this model, we try to describe a few molecular propagation processes. For example, in terms of emission, each bacteria continuously emit molecules at random times with a constant rate. So in this case, for example, it releases the first molecule here, second molecule here, third molecule here. So in this case, we can see the exponential random variables between two consecutive molecules. So this is a random variable, and it follows a exponential distribution according to the knowledge in the probability and the stochastic processes. And for the molecule propagation, the molecules propagate independently, and it also, the molecules are subject to degradation. That means they may disappear after some time. And for the reception, we assume that the bacteria perfect count molecules release, these molecules are released from all bacteria, and then they count the molecules inside themselves. And we know that the expected number of molecules observed by each bacteria is constant after some time. So here we plot the number of received molecules according to as the time flies. And for the decision-making process, we assume that each bacterium makes a decision at the symptotic stage, and then the bacterium decide to cooperate if the number of received molecules is higher than a predetermined threshold, and we denote this threshold as eta. So this is how the bacteria make the decision, and then we also define a decision threshold according to the principle of quorum sensing. In terms of analysis, again, we ignore the detailed analysis here. We just show that in this work, we can see the channel response in this system, in which we derive the expected number of molecules observed at a receiver. And for this case, the asymptotic channel response for the considered circular passive receiver due to the continuous emission is given by these results. Again, I do not provide the detailed analysis here, and also for each of for each of these symbols, it has a specific meaning. Please refer to our paper for this work. And based on this symptotic channel response for each receiver, we consider the expected aggregate channel response at the receiver due to all the randomly distributed transmitter. So given this, we derive the results in terms of this way, which is given by multiple integrations. And based on this, we further derive the expected probability of cooperation for each bacterium, as well as the moment generation function of the number of cooperators. And based on this moment generation function, we are able to evaluate the useful statistics of the number of cooperators. For example, the mean, the variance. This will help us to handle the statistical behavior of the cooperators. Again, please refer to relevant sections in our publication for the detailed derivation. And in terms of the numerical results, we plot the number of molecules observed as the time grows. And here we find that the expected number of molecules first increase, and when the time increases, and then become stable. And this is expected for in terms of the quorum sensing. And then here we show the two types of analysis. For the first analysis, we consider this UCA assumption, the uniform concentration assumption. And in the second analysis, we consider non-uniform assumption, which is the results without the uniform concentration assumption. And we find that these two results almost overlap with each other, showing that the assumption of uniform concentration is accurate. And then definitely when the time grows, this analysis matches the simulation points, because the bacteria will make their decision based on this stable or symptotic region. We can see that the analysis can play an important role to determine the number and the statistics of cooperation probabilities and the cooperators. And in the second figure, we plot the probability of cooperation against the threshold. Remember, we define this threshold as a predetermined value that each bacteria will decide whether it is going to cooperate or not. And we see that our exact analysis is always accurate by comparing the exact analysis with the simulation. We also plot the approximated analysis, and we see that the approximate analysis is also accurate when the threshold is low or when the probability of cooperation is high. So in this range, we can see the the approximate analysis is also accurate. And for this figure, we consider different environmental radii. If you remember what we consider in the system model, we consider a bounded circle, and the environmental radii corresponds to how large or how small this circle is. And we see that when we consider a smaller radius, and that means we decrease the radius, and so in this case, it leads to a higher probability of cooperation, because when we decrease this radius, the circle becomes smaller. This means we have like more, bacteria in this small circle. It leads to a higher probability. So this is how we are going to evaluate the impact of different system parameters for the cooperation. So in summary, in this work, we try to extend the concept of cooperative molecular communication, in which we consider the quorum sensing scenario. And in this scenario, each bacteria acts as a point receiver and a passive a point transmitter, as well as a passive receiver, which can recapture the released molecules. And for this case, the molecules, the derived analysis and the simulation will help us to determine the statistics about the likelihood of the bacteria's cooperation. And this will help us to gain further insights into the collaborative bacteria into the quorum sensing. So this is a summary of our third work in quorum sensing. So now let's look at the next work that we have been doing, in which we categorize the one-dimensional molecular communication with two absorbing receivers. So the key fundamental difference that we have considered here is that we now consider absorbing receivers rather than the passive receivers that we have considered in the previous works. So what is the motivation? We know that the conventional studies on the multi-receiver molecular communication systems have typically assumed transparent or passive receivers for mathematical tractability. And if we consider transparent receivers, we are going to see the independence of received molecules among the observations at these transparent receivers. So for these works, which include the existing work, the early works and our works, we can see the transparent or passive receivers due to the tractability. But in practice, we have to consider the practical property of a nanomachine as a receiver. We know that in practice, the receiver service would typically interact with the molecules that of its interest. For example, the receiver would provide binding sites to absorb or to carry out other reactions with the molecules that hit the receiver. So in an environment where multiple non-transparent receivers coexist, that we are going to see that the received molecules or observations at these receivers are not independent to each other anymore, because one non-transparent receivers would impact the molecules received by other receivers. Because if we consider transparent, then the molecules can be double counted. But if we consider non-transparent receivers, once a molecule is received by a non-transparent receiver, it cannot be received by another transparent receiver. Thus, the observations at these non-transparent receivers are not independent anymore. So this motivates us to examine the impact of the existence of multiple non-transparent receivers. So motivated by this, we start from the very simple case. In this work, we derive the closed form expressions for the fraction of molecules absorbed by two receivers when we have two fully absorbing receivers coexist in a 1D dimensional environment. Specifically, as we mentioned, we consider a 1D environment. We will only consider one transmitter communicates between two fully absorbing receivers. So here is the system. In this 1D unbounded system, we consider there is receiver 1 and the receiver 2 and a single transmitter. There is a single transmitter which is located between the two fully absorbing receivers. So when the transmitter release signals, the molecule will transmit along this 1D line to either receiver 1 or receiver 2. So in this scenario, we classify all possible diffusion paths of molecules into path 1, which goes to the receiver, which goes to the transmitter, we go to receiver 2, path 2 goes to receiver 2, and path 3 goes to receiver 1. And path 1 is for molecules diffusing in the environment, and the path 2 and path 3 are used to represent the molecules that hit receiver 2 and receiver 1 respectively. And we know that if only receiver 2 exists, we can further classify the path 3 as path 3A, which means it represents the molecules that do not hit receiver 2 after arriving at the location of receiver 1, or path 3B, which represents the molecules that hit receiver 2 after arriving at the location of receiver 1. So these are the system model, and we divide the different diffusion paths of different molecules. And for this case, for this system, we derive the fraction of absorbed molecules at the receiver 2 by time t for impulse emission of molecules. And this fraction of the received molecules at the receiver 2 is given by this expression. And if the total number of received molecules, released molecules is fixed, then once we derive the fraction of absorbed molecule at the receiver 2, we can easily know the absorbed molecules at the receiver 1 because it equals to the difference. So the fraction of absorbed molecules at the receiver 2 is given by this expression. Again, in our letter, we provide the derivation of this expression as well as the definition of this function R. So R is the function. It has a specific and somehow complicated expression. And we also consider that when the time t goes to infinity, the asymptotic fraction of absorbed molecules at the receiver is given by this result, where K is the flow of diffusion coefficient. And in this means that we derive the absorbed molecules at the time t and absorbed molecules at time goes to infinity. And please refer to the section 3 in our letter for the detailed analysis. So here we show the numerical results. First, we plot the absorbed molecules by time t at receiver 2 against the time t. We can see that first we confirm the accuracy of our analytical results with the simulation. The simulation is denoted by the circle, and we can see that our analysis meet this analysis, no matter it comes from equation 8 or equation 11 for symptotic case, it matches the simulation when time t goes large. And then we can, in this figure, we show the impacts of transmitter to receiver 1 distance, transmitter 2 to receiver 2 distance, which means D1, D2, and the molecule degradation, like is the value of K on the absorbed molecules on the second receiver. So we plot these different cases by examining the impacts of different distance and the different molecule degradation coefficient on the performance. And it will give us some insights. And we have provided a description of these insights in the letter. And finally, I would like to briefly mention one of our research work, which focuses on the simulation algorithm for absorbing receivers. I know that for Adam's talk, he's going to talk about, I think he's going to talk a lot about how to construct simulation algorithms, but here I just want to give a brief introduction to the simulation algorithm that we have constructed to modeling the absorbing receivers. So in order to construct a suitable simulation algorithm for absorbing receivers, we need to first understand why do we need to study new simulation algorithms for absorbing receivers in molecular communications. We know that, as we mentioned, the existing molecular communication studies typically considered two types of receivers. One is passive receiver, which have no impact on molecule propagation. One is active receivers, which can absorb molecules when the molecules hit the receiver's surface. As we mentioned, active receivers are generally more realistic in describing the chemical reaction and detection mechanism in molecular communication, but it imposes a significant challenge in both analysis and simulation. The simulation of diffusion-based molecular communication systems with absorbing receivers often requires a high computational complexity to gain the accurate results. Specifically, in order to perform the appropriate simulation of diffusion-based molecular communication systems, we need to categorize the intra-step absorption probability. And this categorization is of great significance for the accuracy and the efficiency of molecular communication simulation algorithms. So what is the intra-step absorption probability? So now we can see the absorbing receiver, and suppose this is the molecule's initial position before propagation, and this is the molecule final location after propagation. Again, this happened in simulation. So the intra-step molecule absorption is that the actual trajectory of the molecule may across the receiver's boundary during a simulation time step, even its initial position at the beginning of the time step and the final position at the end of the same time step are both outside the receiver. That means if the molecule is initially here at the beginning of this time step, and this is the final location after the propagation, although both of the locations are outside this receiver, its actual trajectory may across the boundary and go inside to the receiver during this simulation. And if this happened in the nature, the molecule would be received. But in the simulation, this molecule is identified as a non-captured or non-absorbed molecules if it's the initial position and the final position are outside the receiver. So in conventional simulation algorithms, a molecule is absorbed if it's, to deal with this problem, in conventional molecular simulation algorithms, a molecule is identified as absorbed if its straight line trajectory within a time step cross the boundary. For example, that means the straight line from the initial position to the final position. If this straight line across the surface, it will be identified as absorbed. In the refined Monte Carlo algorithm, the RMC algorithm, the intra-step absorption probability for spherical receiver boundaries is approximated as the probability for a fully absorbing receiver with an infinite planar boundary. But given this assumption, it only provides an accurate simulation result for a relatively small time step length. And we know that if the time step length is very small, the simulation will take a long time. So based on the observation of the existing simulation algorithms, we find that they all follow a common structure, and we summarize the structure here. So here I don't want to repeat this structure, but I just want to say that the different algorithms have a common step, which is to determine if the molecule is absorbed, but different algorithms have different determination criteria. So in this case, in this work, we can see the 3D model, and in this 3D space, there is a diffusion-based molecular communication system. We can see the point transmitter, and then we can see a fully absorbing spherical receiver. And we also define the radius RR, the receiver's boundary as the omega R, and D is the diffusion coefficient. We assume the transmitter releases N molecules. And once these molecules are released, the molecules diffuse in the environment until they hit the receiver's boundary. So in this simulation algorithm, how do we deal with the intra-step absorption probability. We propose a new a priori simulation platform to approximate the fraction of molecules absorbed as a fully absorbing receiver when this coefficient is large. And here we focus on the case that this coefficient is large. It corresponds to large delta t, which means the large simulation time step, or smaller RR, which means the smaller receiver. And for this case, it has its own benefits compared to the existing simulation algorithms. So the procedure of our proposed scheme is that we first calculate, before the jth molecule diffuses, we calculate the probability that the molecule is absorbed in the current time step. And this probability depends on the distance between this molecule and the center of the receiver, and as well as the simulation time step. And the calculation we provided is here. Then we decide the molecule absorption by generating a uniform random variable. And for this random variable, we compare it with this calculated probability. If this random variable is smaller than the probability, the molecule is marked as absorbed. After this, each not yet absorbed molecule is propagated according to Brownian motion. And if any of the not yet absorbed molecule is inside the receiver's boundary at the end of the current step, we will revert the diffusion of this molecule and let it propagate until it diffuses to a location outside the receiver. So this is the procedure of our proposed algorithm. So the key idea here is that we generate a uniform random variable, and we mark a molecule as absorbed one if this random variable is smaller than the probability. And after this, we perform the simulation as per some procedures. So as we mentioned, we would like to see that our algorithm achieves a higher accuracy for the large coefficient according to larger time step or smaller receiver radius. So we can see that when the simulation time step is large, we can see our proposed APMC scheme achieves a much better performance than the existing RMC scheme and the SMC scheme. So our observation is that when the simulation time step increases and other parameters remain the same, our algorithm becomes more accurate. This is what we expected. And then we also consider a smaller receiver, and we can see that when we consider a smaller receiver with a radius of 0.5 micrometer, we can see that when the receiver's radius decreases, our algorithm becomes much more accurate than the existing RMC algorithm. Again, this is expected, and this is our benefits of our proposed APMC simulation algorithm. So here I just briefly introduce the procedure and the key idea about one of our proposed molecular communication simulation algorithms. And I do believe Adam will talk more results about how to construct the effective simulation. Then I would encourage you to listen to his presentation if you are interested in how to construct effective and appropriate simulators for molecular communication systems. So at the last slides, I'm going to introduce a few future directions. We know that there is a long way to go to apply the theoretical molecular communication research outcomes into the nano-scale applications and bring these applications into reality. And in this slides, we have provided a summary about my research work in terms of cooperative molecular communication, carbon sensing, the 1D molecular communication with absorbing receivers, and the simulator construction. And look at the future, we have some research challenges that we need to tackle. The first is always the theoretical modeling. We know that the existing results for tractability, they always adopt some idealized assumptions. So in this case, we need to construct practical theoretical modeling by relaxing these idealized assumptions. For example, we have to consider realistic transceivers and the boundary of the environment. And in this environment, we also need to consider practical properties such as the flows and the chemical reactions. And based on this modeling, we also need to consider or investigate the synchronization, channel estimation, and inter-symbol interference cancellation with this theoretical modeling in molecular communication, because they are quite important problems in the nanoscale applications. And after that, we would like to propose new validation methods to verify our theoretical results. For example, we need to speed up the particle-based simulations. Currently, the particle-based simulations takes a lot of time. Also, we always want to get some test bed, micro scale, or even macro scale test bed to validate the results. And ultimately, we would like to perform the experimental validation by collaborating with biologists and nanoscientists. This will significantly advance the field of molecular communication and bring us a lot of benefits for realizing the molecular communication enabled applications. So I think these are the key challenges which can be tackled based on what we have introduced in these slides. So I think this is the last slide. And again, at the end, I would like to say a big thank you for all the attendees, for all the listeners, for the audience, and pay special thanks to my students and collaborators. If you have any questions regarding these slides, please feel free to contact me or directly contact the students involved in these research works. And I wish you a lovely day and enjoy the remaining of this workshop. Thank you very much.